And then you've got left what was bound. You knew how much you had to start with. You can get the ratio. Some proteins do change color a little bit. Their UV absorbance changes. Not enough to really quantitate, but enough to say, hey, it shifted 30%. Right? So in practice, for no other reason than like real practical concerns, it's often easier to get the fraction bound than the actual amounts. And if we wanted to express what that fraction bound is how much of it is bound out of the total. And the total is what's bound and what isn't bound. Right? This goes back to our marker analogies. If I want to know the fraction of markers that have a cap, I have 2 markers with a cap, and my total is 2 markers with a cap and 1 without. 2 out of 3, 2/3. So I can figure my ratio, right? So
is it just the part over the hole?
Yep, just the part over the hole. You got it. So we just defined that, but here's where we get tricky. This is the best part. Again, this just seemed to trade one problem for another. Because I just said the whole problem was we can't measure these damn things. And we just wrote a new equation where you have to know the values of these things. I'm going home. But here's the smart thing. If we pull back our original equation, our KEQ equation, and we want to solve some of these things, we can just do algebra. So watch the rearrangement. I'm going to rearrange this in terms of PL. And I'm going to find out the concentration of PL is, I have to multiply both sides by the denominator, is KEQ times P times L. And then I'm just going to substitute that in everywhere where PL occurs. And that's what happens right here, is that this theta equation, everywhere where PL occurs, we just put in the algebra. And we get theta equals K equilibrium times P times L. I don't know why they switched the order there. It doesn't matter. Multiplication. Divided by KEQ times P times L plus P. Plus P is still dangling there. And then we just simplify terms. Notice that every single term here has protein concentration. So just divide the top and the bottom by protein concentration. Poof, it goes away. I want to do this explicitly, even though it's not there, to make it really clear. I think it's really magical what comes out here. Again, notice all I did was I took this, and everywhere where PL occurred, I substituted it. And then I notice every single term has concentration of P. So I'm going to cancel them all out. Replace it with 1. Canceled, canceled, canceled. Yeah. Now that looks like an eye. Then we noticed that KEQ occurs in most of the terms. So let's divide every term by KEQ. KEQ divided by KEQ cancels out to 1. KEQ divided by KEQ cancels out to 1. Oh wait, this term didn't have a KEQ. But we still got to divide by KEQ, because we divide everything. Well, 1 times 1 times L is just L. 1 times 1 times L is just L. And now we have this 1 over KEQ thing. This is not as super helpful for us, because you have to do like inverted, and it's hard. So lazy biochemists said, you know what? 1 divided by KEQ, we're just going to define as KD. It's a new number. 1 over KEQ. It's KD. It's fine. Don't worry about it. But it turns out it actually has a huge impact if we think about units. So check this out. Okay, let's go back to our KEQ. What's the units of protein ligand? What would a unit be? Molar, right? What's the units of this? Molar. What's the units of this? So what's the units of KEQ? Inverse molar. excuse my language, what the hell is an inverse molar? Well, yeah, it's 1 over molar, but if I'm looking at a test tube, can I ever point to an inverse molar? I don't even know what that is. That's just a math thing. It's not a real thing. What's the units of kb? This is 1 over molar.
That's molar.
Molar. Kd is back to units of something I can measure. I can look at a test tube and be like, that's molar. I can measure that. So we're lazy enough, we're like, math. Turn it into units that we can measure. And we end up with this equation. Theta equals ligand over ligand plus this new constant we define. And look at how magical this is. Just with algebraic trickery, I don't even have to know how much protein I have. I don't have to be able to measure my protein. I want to know how something binds iron. All I have to know is how much iron I poured in the test tube. I don't care how much protein's there. I've eliminated the things that are hard to measure. The ligand is what you pour in the test tube. It's the binding chemical. It's the drug. How much drug did you inject in the patient? Well, is his immune system going to bind it? Well, how many immune cells does he have? We don't know. We don't care. This equation is only dependent on the ligand and some intrinsic factor, some number. And it turns out that number basically tells us how well the protein binds. Because that's the only knob we have. Let's say we have 3 proteins in our body that bind iron. How do we know which one binds iron best, which one binds iron worst? If we look at the equation, the amount of iron we add is going to be the same for all of them. We have all 3 in a jar, we pour in iron, that's the same. The only knob they can differ by is this Kd. And so we call Kd a lot of things. We call it Kd. This technically stands for dissociation constant. Constant. But more commonly, it is called the affinity. This protein has high affinity for iron. This protein has low affinity for iron. What do we mean by affinity? We mean that number. That number tells us how well something binds. Yeah?
So when you're saying it's called the dissociation constant, is it a constant for each ligand or each
protein? It is a constant for the protein. Well, actually, let me be even clearer. It is a constant for the protein to that ligand.
Just the equation.
Yeah. Well, so for example, let's say I have a protein that binds iron. It might have a very good binding to iron. Expressed in Kd, a very good Kd, right? That protein doesn't bind DNA for shit. It has a very bad Kd for DNA. So it's a relationship of a protein to a ligand. In theory, every protein has KDs for everything in the world, but hemoglobin's KD for Jupiter is pretty bad, right? Doesn't get to bind Jupiter very often. Right? Everyone's a potential friend, just most people are very small on the friendship axis. Okay, so full disclosure, you need to burn that equation into your retinas. It is more important than the Henderson-Hasselbalch equation. It is going to be your love and your life for the next 10 weeks of class. Yeah?
Why doesn't the ligand
This has to do with the fact that it's a denominator here. We can't separate these terms. You could rewrite it. You could do 1 over 1 plus 1 over Kd times ligand. That'd be like a way to rearrange it or something, but I don't know if that would buy you. But the reason we just couldn't cancel them out right away is because when you have a complex denominator, you can't cancel them the same way. We can play with it, that's fun. But so this is going to be important. And if we put this into a real example, let's talk just theoretical math for a second here. I'm going to put this for this, make it simple. Let's talk math here. We always have L on top and L on the bottom. The KD varies. So let's put in some arbitrary numbers. Let's say L is 10, and right? if KD is 1, just put in an arbitrary number, small, KD is 1, what's this guy? Less than 1, 10 over 11, right? Less than 1. But pretty high. I mean, what's that? That's like 91% or something? 91% bound. That's not bad. Good so far? Let's put in a different number. What if my KD wasn't 1? What if my KD was 100? I'd have 10 over 110, which is 9%-ish. So notice this weird dichotomy, this inverse behavior. The smaller your KD, the better you bind. The bigger your KD, the worse you bind. Small KD or binding, because it's a dissociation constant. Large KD. Good. So, numerically speaking, the smaller your KD, wait, I did that backwards.
Yeah.
Oh my gosh!
You got us confused, man.
You were keeping us on our toes.
No!
I'm trying to figure it out.
Thank you. The smaller the KD, the better the binding. The larger numerically the KD, the worse the binding. This, by the way, has a relationship. It has to do with, ultimately, the fact that things associate on log scales. You can think back to the Henderson-Hasselbalch and pH, where lower pH means more hydrogen, right? Lower pH means more hydrogen. It's the same kind of inverse relationship that we see. And actually, if you get into the fundamental pChem, they come from the same reason. So that's kind of funny. This is confusing enough, but biochemists had to go and make it just that much worse by being lazy. So if you ever start reading biochemical literature, like you go and read a new paper about a new drug, you'll see terms like high affinity interactions. When biochemists say high affinity, what they mean is small KD. They don't mean a big KD, because that would be crappy binding. They talk about the functional side. They say high affinity, which means teeny, teeny number, just to keep you on your toes. And low affinity interactions mean a big number. Ah! Yep, yep. Km is actually a derivative of Kd. We're going to get there. Right. We're going to start with fundamentals. Why carbon, right? So that's our binding equation. And the thing that I always like to remind people is this is just math, right? I could write this a different way. I could say y equals x over x plus some constant, right? It's just an equation like that. And the interesting is any equation of that form, where y equals x over itself plus a constant, takes a certain shape. That shape. And that shape is called a hyperbola. Or we could call this hyperbolic binding. And here's where, like, science, like biochem, gets exciting for me again. It turns out that this equation governs every interaction of proteins with ligands. And remembering that this curve is what's happening in every single interaction in your body can make a lot of things make more sense. So let me look at one. Aspirin works by binding to a protein in your body called cyclooxygenase 2. It also binds to cyclooxygenase 1 and makes your stomach bleed, but that's a whole other story. So look at this. I have a bad headache. I take, L here is now aspirin, my ligand. I take one aspirin, and the amount of pain relief is pretty big. I take a second aspirin, and the amount of additional pain relief is pretty big. I take a third aspirin, and it barely helps at all. And I take a fourth aspirin, and it barely helps at all, and I start to poison my liver. Why aren't drugs linear, right? They're not. Like, you can't just be like, one aspirin helped my headache, so 10 will make it much better. There's a dropping off. There's a diminishing effect. And it's because all these interactions are governed by this equation. The first few steps are dramatic changes before it plateaus out. We see that with every drug we take. We see it with our satiety and fullness. Eating a big meal can fill you, but you still have some room. You never quite fill up because it kind of plateaus out. There's always a little bit more you can eat, right? At least for me, there's always a little bit more. But truly, to me, it's transformative. Every interaction, food, drug, my natural endorphin highs, they all obey this curve. The first little bit is very dramatic, and then it plateaus out. Why is it hard to get that heroin rush again? I'm sure we've all felt that, right? Sorry. That was funny. If anyone here is actually fighting heroin addiction, I salute you. That's hard stuff to battle. I won't make light of it. And so that's the kind of curve we get. But mathematically speaking, we have a problem. Any curve of this nature has an asymptote. It has asymptotic behavior. That is to say, it'll never, ever, ever reach 1. And this is really easy to show in the math. Make L 10 jillion. I don't even know what a jillion is, but it's a big number. And your KD 1. Your number is 10 jillion over 10 jillion plus 1. It'll never cancel out. There will always be a bigger denominator than numerator. No matter how far you go and how high you go, it'll never hit 1. You cannot saturate. Which makes it really hard to measure and talk about it. Because normally we'd be like, well, how much does that glass hold? Fill it with water to the top and tell you. Now we have a system that you can never fill to the top. How do we talk about it? How do we say it? And so we actually rely on a math trick to communicate this. We pointed out, so let me go back to just 10 as opposed to 10 jillion. If my ligand concentration is 10 and my KD is 1, we get this 91% bound. What if my KD is the same as my ligand concentration? If it's 10, then I have 10 over 20, half. It turns out that another way to think of KD is the 50% point. Where are we? Oh, the pKa is the 50% point. We're going to see this crop up in every equation in chemistry over and over. The KD is where we're 50% bound. And that's easy to measure, and that's easy to work with, and it all falls out. And yay, life is great. Good stuff there?
So is it directly related to pKa then, or
The fundamental math that relates them is the same. And if we have time, I'll try to show you why, but I don't want to do that yet, because it'll be bad. What I do want to do with the remaining time we have is do some examples and some questions to show you how this works and why we care. Because this is like really important and key. I'm tapping my nose, like this will matter.
can you send us email questions for?
I will, and I've realized I need a few more, so I'm going to send some new questions too. So let's take an example here. Let's assume that Dr. Bonham has a neighbor named Dusty. This is easy to assume because I have a neighbor named Dusty. Nice guy. Installs solar panels. But, and this is not true, let's assume Dusty has a terrible disease. I don't wish that on him, but let's play with it. Let's assume Dusty goes to the hospital and he's having terrible problems. And what they find out is that his blood sugar, his cellular sugar levels are really low. He's not getting enough sugar into his cells. And they managed to find out that a protein called hexokinase, which has a role in getting blood sugar turned into cellular sugar, that is sugar inside your cell. We're going to learn all about hexokinase, so don't worry, this is just a preview of things to come. It has a role in helping take sugar out of the bloodstream and put it inside your cell for digestion. And they managed to figure out that his is not working very well. But to confirm